In 9.1d, we're going to understand the relationship between the significance level of a test, the type 2 error, and the power of a test. So I first need to define what power means, and here's what it is. The power of a test against a specific alternative is the probability that the test will reject H sub O at a chosen significance level of alpha, when the specified alternative value of the parameter is actually true. So I will tell you, power at first tends to be one of the trickier things in this book to understand. We're going to spend some time on it, so hopefully this will start to make sense as we talk through it. Let's look at this specific example here. In this case, our hypothesis is that the true population proportion is 0.8. However, we really think it's greater than 0.8. In fact, after we did more analysis, we actually found that the true proportion was really 0.11. So here's the question. When we do a hypothesis test on here, what is the probability that we actually will end up rejecting H sub O and concluding H sub A is true when we know this is really the true proportion? Technically, we should have never had 8% there. We should have had 11. How powerful is this wrong test to truly allow us to say we're going to reject it and conclude this, which will still be okay. It'll cover our butts because the real answer was 11. How powerful is this test, again, to catch that that really was the right answer? That is what power is. So by definition, here's power again, another way to say it. It's the probability the test will reject H sub O at a chosen significance. So the power that we're going to reject this at a chosen significance, but be careful when a specified alternative was actually true. In this case, 0.8 wasn't true, it was really 0.11. So let me show you a picture of it, because I think the picture is really where you see power. Every hypothesis test has a normal approximate curve we can do. So I'm going to do a normal curve, and the true population proportion is 8. So that's right smack dab in the middle. So that's where it has to be, because that's our mean in this case. Now, we chose for this, it looks like in this picture, an alpha of 0.5. So let me just jot that down. In this case, we have an alpha of 5%. Now, notice this is a hypothesis of a greater than, so the 5% goes on the higher end, the right part of the tail. So if we draw this down, we would get that this is our 5% region. This is where we would make our type 1 error. Now, I thought this was the right graph, and I was hoping I'd come in and say, hey, I reject H sub O and I conclude H sub A. I conclude that it's actually higher. But I was wrong. It should have been 11%. So I'm going to actually sketch the normal curve with the right mean below this. I'm going to still kind of use the concept of the number line, though. So keep in mind, look at this, because this is where 0.8 is. Notice 0.8's on my curve going to fall right below it. This is still the same number line, just continued. So follow that. Again, the 0.8 is right there. If I draw it, I really think that the mean was at 0.11. Okay, this is where it should have been, was the 0.11 right there. So if this curve was the real one, how powerful was our initial test, which was this guy, to actually capture that this was true? Well, all you do is this. You take your alpha again of 0.5 and you continue down. This right here, the area under this curve, is called the power. So what you're going to see, type 1 error. We have the power, and they found for here it's about 0.75 or 75%. Now, the other thing is the type 1 error. Remember we talked about as this type 1 error, if it gets smaller, the type 2 error gets larger. Well, imagine this line, by the way, if it had been drawn, how about we go a little bit further? If we go this way, our type 1 error would have gotten smaller. Type 2 is going to get larger. Well, where you see the type 2 error, folks, is actually on the alternative curve down here. So we have the power at 0.75. The type 2 error is its complete complement over here. So type 1 shows in the initial analysis the type 2 and the power are complete complements of each other, but related to the alternative hypothesis. So let's talk a little more about power in type 2 error. Another way to kind of talk about the power is to say this: power of a test against a specific alternative. Again, how powerful is this test up here that we did, that P was 0.08, to really test a specific alternative? It really should have been 0.11. So how powerful is it? The power is going to be shown down here. If you want to look at in terms of probabilities, power is this. What is the probability to reject H sub O, which is right here, given the alternative is true? Our alternative was down here. So the probability that we actually rejected H sub O above in our our real test, but given that this alternative down here was true, that's where we see the power in here by definition. Well, another way to look at that power is to say, why don't we take the whole graph and of 1 and actually subtract this little piece from it? Which again, this was called, remember, the type 2 error. So if we have 1 minus this red portion, it's the same as the power. So another way to state this one would be 1 minus, well, this portion, what this is, remember, type 2, I failed to reject H sub O given that H sub O is false. That's a type 2 error. So I'm just going to rewrite that as 1 minus type 2, which means you might see this notation, 1 minus B is just a shorthand saying that this is the type 2 area. So ultimately, by definition, what power is, another way to find it, is if you know your type 2 error, it's 1 minus your type 2. Because these two elements make up the entire alternative curve down here of what we think the true hypothesis really should have been. It's important for you to understand how power changes as significance levels change, as sample sizes change, and things of that nature. So we're going to investigate some scenarios. We're going to go back to the fast food example. Remember, they wanted to be faster at the fast food drive-through. They currently were at 63% of getting their customers through in less than 2 minutes. He's hoping with more employees on the window, it's going to go less than that. So what I'm going to show you here is above here in the black and the red is our actual hypothesis. That's what this is right here. We are choosing an alpha level of 10%. So if this is the true hypothesis, and if this is our line for alpha, so remember, if this is here at 10%, then what I clearly know, this is my type 1 error. So if I know the area of that curve, it's type 1. Well, what if, remember, P is less than, so I think the true hypothesis shouldn't have been at 0.63, it should have been smaller than that. I think the true curve should have been more to the left of this, so I think it should have been over more, okay? If it's over more, it would have been here. Fine. Continue to draw your alpha down at 10%. Well, remember, by definition, this shaded region here is the power. So if that's the power, don't forget too, that's your type 2 error. This slide is really addressing this question here, significance level and power. What happens if I change the significance level to the actual power down here? Well, what you're going to see is I actually did an analysis where I had the significance at 10% and I changed it to 1%. Well, one thing we know, if this is 10%, if we move it to 1%, it's going to go right down here. Clearly, the type 1 error went smaller, which made sense. Remember, if that's type 2, we said if type 1 gets smaller, type 2 is going to get bigger. We can see that the type 2 got bigger. Well, what about the power? The power of this actually went down. You can see that right here where the simulation computed the power. Here it said that this region right here was at 97%. When it redid it, it went to 81%. So what conclusion can we make is this: that as you lower the significance, or alpha, you ultimately are going to lower the power. I think another real easy way to actually remember this connection with significance is this. If we lower the alpha, we know that the type 1 error will get smaller. Well, if type 1 error gets smaller, we know type 2 error has to get bigger. Well, if the type 2 error gets bigger, 1 minus a bigger number will cause the power to actually go down. So let's just make some conclusions about significance and power. And I'm going to start with this one because we just did it. Decreasing the significance level is going to decrease the power of the hypothesis test to detect the difference in the hypothesized and the actual parameter. What that's going to do is it's going to cause the type 1 error to go down, and thus the type 2 error will go up. Well, what if we increase the significance level? Well, if we increase the significance level, I'm actually going to go here. If we increase significance, means the type 1 error goes up, which means type 2 error goes down. If type 2 error goes down, I'm just going to think about this. If type 2 goes down, that means the power just went up. So it's almost easier just to almost think of this formula in how type 1 and type 2 are related. Let's look at another scenario. Our sample size and power are related. So again, let's just look at our same situation. We had our proportion at 0.63. We think it's going to be lower. Let me show you how I changed this. In this first example, our initial sample size was 250. I lowered the sample size to 100. So remember what happens if you have a smaller sample size with your variability. Recall, a higher sample size gives you something that's more stable and less variable. A smaller sample size is going to have more variability. So imagine this. What if we had the shape of this initial curve looks like that, with a good sample size of 250. If I lower the sample size, this curve is going to get more variable. This curve is actually going to spread out more. So what that means is it's going to actually pull this tail out more and this tail out more that direction. Now, keeping your significance here, if it gets pulled out more, what you see is something like this. With that, this significance level, I still have to keep it at 5%. It's going to be too high, so the significance level actually ends up getting moved a little bit over too, like that. When it does it, look what happens. I have to keep my same percentage here, but it cuts off some of that power. So in this example, what you see is the power is actually being reduced. And that's what happens. You're going to see if you reduce your sample size, you're actually going to see the power of the test will reduce also. So the connection I like to make is I reduce n, it's going to cause a smaller sample size but higher variability. That variability in turn is going to cause more spread in the actual initial curve, which is then going to reduce our power. Let's make a few conclusions with that. Decreasing the sample size, again, we just said will decrease the power. Conversely, if you increase the sample size, you're going to increase the power. I will tell you for sample size, yes, there's a way of how it all kind of churns through, but just think of it logically. We know a larger sample size reduces variability, and it just makes it a stronger curve. Well, same thing. A larger sample size just gives you more power within it. Now, let's just talk about this last part here. What if you insist on having a smaller significance level? Well, remember, your smaller significance level is going to cause your power to go down. Well, if it causes your power to go down, but you want the power really where it should be, how do you maintain a powerful study if you lower significance? Easy enough. In order to get it back up, you have to increase your sample size because that will increase power. So the way to maintain your study if you want to lower significance is to increase your sample size and hopefully have a net zero impact. Ultimately, larger samples are always a good thing to have, especially if you want to maintain your power. Now, again, remember this study. What if, with that manager having all those extra employees, thought things were making a difference, so he wanted to come in and say, you know what, I'm going to reduce this true proportion. It shouldn't be 63%. True proportion should be reduced. Well, by reducing the true proportion, what does that do to the power? Again, here's our initial scenario right here. I'm going to show you we are at a 10% significance, sample size of 250. Here's actually a second scenario where I've reduced our proportion. So it's a brand new one, but I kept the significance at 10% and the sample size at 250. What happens to the power if I actually reduced our population parameter? Let me show you the two hypotheses first. This right here is the initial one where it is set up at P is at 0.63, but I really think it's at 0.53. But I'm saying here, what if I reduce that 0.53 because I think it's even lower? Notice the P is still at 0.63, but I reduced our alternative to 0.5. So from 0.53 to 0.5. So this alternative has a proportion of 0.53. This alternative has a proportion of 0.5. Well, think about it logically, folks. This is our initial hypothesis that we had about the 0.63. If this is the alternative that we think it should be 0.53, this shows our power. But I really think it should be at 0.5. Well, fine. To make this curve have its center not at 0.53, but at 0.5, what did I have to do? This curve had to be moved to the left. When you slid this to the left, you actually got yourself a little bit more power. So this tail here that shows black moved over, and a little bit more of that type 2 error actually became power. So when you reduce the population parameter, again, we're thinking it's really 0.53. Nope, now we think it's 0.5, even smaller. What happens is you actually end up increasing your power. On the flip side, what if we increase the population parameter? Well, if this is 0.53, if we moved it to 0.6, this curve would have to move over to the right. Our power would be reduced. Well, just look at this question here. It says, how should the sample size be changed in the second scenario to get back to the 97%? So this was just our first scenario, which came in at a sample size of 250 with an alpha of 10. This here, what we did differently. So let's piggyback off that last example. This is actually here, again, our initial hypothesis of the 0.63. Where we think the alternative is really 0.53. This one is at 0.63, but now remember we thought it was really 0.5. So what we did is we lowered the alternative, which increased our power. So we were at a power of 97%. Now we went to a power of 99%. Here's my question for you. I want to get back to 97% of power. How can I do that with my sample size? Well, you just have to remember the impact of that one. When you reduce your sample size, you reduce your power. So if I lower my n, it's going to cause my power to actually lower. You know, what if you wanted to do it with a significance level? It's a second question. How on significance levels, if I need to actually reduce power, think about it again. 1 minus type 2, right, is our power calculation. So if I want to reduce power, I would increase type 2. If I increase type 2, what I would do is reduce type 1. How do you reduce type 1? To reduce type 1, you would actually lower your significance. A key thing to know about power is this, is that any significance level or desired power. Being able to detect a small difference between the hypothesized and actual parameters requires larger samples than detecting a large difference, which requires smaller samples. Let me just show you what this one means because it gets a little confusing. The first statement here, to detect a small difference between the hypothesized and the actual, we need a large sample. Right here, we have 0.63 is our hypothesized, 0.53 is our alternative. Now in our second example, we have 0.63 is hypothesized, 0.5. So here there's a smaller difference, here there's a larger difference. Both of these two examples I'm showing you have the exact same power level. So what do you notice? When there is a smaller difference between what the real alternative should be to get the same power as when there's a larger difference between here. Here you have a sample of 250, here you have a sample of 150. So when they say detecting a larger difference, which is this guy right here, you need a smaller sample size, which is 150, to maintain the same power. In comparison to this one, where there was a smaller difference between the hypothesized, we needed a larger sample. We noticed it had to go to 250 to maintain the same level of power. Let's wrap up this entire hypothesis process. So remember from day one, the first thing we actually talked about is we need to make a claim, state a hypothesis. So we start by doing a null hypothesis of H sub O and an alternative of H sub A. When you do that, you have to decide though, is it one-sided or two-sided? H sub O, it's called the no difference. It's kind of our starting point. H sub A is actually what we expect. So if we were to ask the proportion of AP students who sleep 10 hours or more, okay? If I ask that, I might say the true population parameter is 60%. I think it's less than that. I think fewer than 60% of AP students sleep 10 hours or more. So this is a one-sided hypothesis where I think H sub A is going to happen. So what do you do next? Well, now you test your evidence. You actually do the significance test. We have to get the p-value. By definition, p-value, it's the probability that the test statistics results happened given that H sub O is true. What is the probability of that? Well, once we have that probability, we compare it to the significance, which is alpha. And remember, if you're statistically significant, it means your p-value is less than alpha. And when that's the case, you reject H sub O. Okay, when you make your conclusions, you need to decide what type of conclusions to make. So one conclusion you can make is this. If your p is small. So if p is less than alpha, you reject H sub O and conclude H sub A. But what if it's large? Well, that means if p is greater than alpha, you fail to reject H sub O, and you cannot conclude that H sub A took place. Okay, now some things you have to be cautious of. There is always going to be error due to variability in the data collection. There's two types of error. Type 1 error is when you reject H sub O when H sub A was true. Now, type 1 error actually equals the alpha level that you chose. Other type of error. Type 2 is when you fail to reject H sub O when H sub O was false. Now the last part is bringing in power of the test. So the power of the test means this. What is the probability you reject H sub O given the specific alternative is true? How strong is our test in our H sub O setup that we will reject it if a different alternative is true? Well, remember to find the power, another word for it is 1 minus your type 2 error. Why is that? Take a look at this graph here. This is our original hypothesis. In our original hypothesis, we've defined here that the proportion is less than, so we're going to look on the left-hand side of our curve. We're going to drop our 5% for our alpha, which means this little 5% here is our type 1 error. Type 1, we're going to reject H sub O when we shouldn't have. So this region is you fail to reject. Now, we think the true alternative is less than 60%, so it's going to be moved over to the left from where 60% is. This is really the true curve. So continue your alpha. When you do that, what that tells you, this is the power of your test. So this is the power to reject H sub O, because this is the H sub O rejection region, and so is that, given this alternative is true. Now, because power and type 2 are complete complements of each other, if you know type 2, you can compute the power and vice versa.